Hi there, my name is Raymond Doe, and welcome to my Physics 2212 Lab 3 video, Magnetic Field of a Bar Magnet. Hope you enjoy. The purpose of this lab was to graphically and significantly determine the distance dependence of the magnetic field produced by a bar magnet. To accomplish this, we will employ the principles of the Biot-Savart law to measure the distance dependence of the on and off axis magnetic fields. In this lab experiment, we will firstly analyze the magnetic fields on axis and perpendicular to the bar magnet using a magnetometer app before constructing the computational code to generate a visual representation of our observed model and data. Bar magnets have an essential quality about them due to their nature as magnetic dipoles, meaning that one end of the bar emits a positive magnetic field while the opposite emits an equal but negative magnetic field. The movement of the total field flows out of the north end and into the south end, with a dipole moment pointing in the direction from south to north. The fundamental physics concept used in this lab experiment is the Biot-Savart law, which in physics is a fundamental quantitative relationship between an electric current I and the magnetic field B it produces. The law includes several equations applicable to various current-carrying objects such as point charges, wires, loops, and in this case, dipoles. To the right, we will find the relevant formulas that will be useful to us in completing this lab experiment, such as the magnetic field of a bar magnet, the linearized version of that equation, and the magnetic field off-axis of a magnetic field dipole. Here is merely a preview of our results from our computationally generated simulation of the magnetic fields from the bar magnet acting on the magnetometer in this lab experiment. With the magnetometer as our system and the bar magnet and Earth as our surroundings, we will use a meter stick, phone, and tape to locate the magnetometer sensor on my device and measure the bar magnet's magnetic fields at various distances on axis and perpendicularly off axis of the bar magnet. As the magnetometer moves closer to the bar magnet, the measured magnitude of the magnetic field increases. Due to distance dependence, the relative position of the magnetometer has no effect on the measured magnetic field. This slide shows my Excel sheet in which I have recorded the various distances on and off axis of my magnetometer in relation to the bar magnet and the calculations of the net magnetic field having been corrected to exclude the magnetic interactions from our planetary dipole. In the line graph to the right, we will be using the values of the slope and y-intercept of this line in our calculations of mu in our next step. In this lab experiment, there are generally 3 steps to the calculations process in order to yield the values that will be important for us later. In the first step, we're algebraically solving for mu by manipulating the equation for the field of a bar magnet and the field of an on-axis dipole. Secondly, we'll be using the linearized equation of a bar magnet field and substituting the slope value from the graph for n and the y-intercept for k. Third and lastly, we'll be plugging in our known values back into our equation for mu, and all of these values will be useful for us in our computational code coming up later. This slide simply displays the most important segments of my GlowScript computational code, in which I calculated the expected net magnetic field and generate a visual representation of the magnetic fields acting on the magnetometer at various distances and positions. Finally, we have our results in the form of a visually simulated representation of our magnetic fields on axis dipoles, which is in red, the perpendicular axis dipoles in blue, and our off axis dipole in purple. Below this, we have some relevant values, but most importantly, we have the magnitude of the magnetic field at 45 degrees at the distance 2.23576 e to the negative 5 meters. In comparing the data from our observed model versus our computed data, we can see that the net magnetic field of our observed model is slightly larger than our computed field. The largest sources of potential error that may have compromised the integrity of my lab results may have been the imprecise location of my magnetometer on my phone, or the magnetometer not properly finding north, thus having the Earth's magnetic field alter or skew my data. If the magnetic north had not been considered, the dipole effect of the Earth's magnetic field would have certainly influenced our findings and calculations. The K value, mu value, and B values will all vary. Attaching 2 identical magnets end to end would not alter the direction of the magnetic field, with the mu hat still pointing from south to north. However, the magnitude of the amassed magnetic field would certainly be amplified. Thank you for watching and have a great day.